Okay, I'd like to introduce my co-chair for the session, Pascal Lee, who will be talking about Human Return to the Moon, a Mars-forward analog strategy for lunar science and exploration. Take it away, Pascal.
Thank you. Given that we are returning to the moon, the idea to convey here is that if we are also committed to going to Mars afterwards or somehow as part of the process, we should have this in our minds and in our planning sort of from the get-go. And as this might seem obvious, that we should just simply bear in mind that we should be going to Mars as well, and therefore we should do things that are consistent with both the moon and Mars whenever we can, I would not take it for granted that it's going to happen on its own. So the suggestion here is that we should maybe identify a process, maybe a mechanism, to somehow ensure that as we return to the moon, we are also thinking very specifically about how our decisions in this return will affect what we might do on Mars or enable things that we want to do on Mars. This is not particularly tied to any current plan in a specific way. Things are still in flux. We are, of course, thinking of a orbital lunar gateway. There's also the thought of a lunar village. But I'm going to suggest that if our goal is to explore the moon or Mars in depth and over the long term, then you really have to try to meet two objectives at the very top level. One is you want to have a sustained human presence on the moon and then on Mars. And number two, beyond the ability to stay there for a long time, you want the ability to essentially reach all other parts of your planetary body. So we want a global exploration reach on the moon and Mars. And if you sort of look at this little mini traceability matrix, the requirement for objective one is to essentially have a permanent base. And I'll try to justify that in a second. And the other, of course, is to rely on local resources as much as possible, but above all, water, since it is such a useful resource potentially and a heavy one. So, but I don't think necessarily that we should be reliant on water ISRU from the get-go in our operation. But on the other hand, we might decide to choose the site for our permanent base based on that potential. The second requirement, or the third requirement, is often overlooked, which is the fact that it's not just a matter of setting up a base. You want to have a multi-range mobility system, so the ability from that base to radiate out to all the sites of interest that you want to explore. And this is really to avoid the sortie mission approach to our return to the moon, in which you would sort of land at a different location each time. In the short term, it will maximize science return. It will keep it super interesting, but in the long run, it's a bit of a losing proposition because you're not building an infrastructure that allows you to stay and do work in the long term. So it's not just a base that you want to set up, it's a base near water, plus equip yourself with a multi-range mobility system on both the moon and Mars. Now, the best, of course, example that we have for this is Antarctica. We have a giant piece of real estate to explore scientifically. The strategic approach here is to set up a logistical base. It could have been pretty much set up anywhere, sort of to first order, but of course you want that place to be particularly interesting logistically, so you want to be able to resupply it by sea. That's why it's a coastal site. You want to make sure that it's sort of a safe area to land, so a good harbor, for example, and maybe, as a bonus, have sites of scientific interest in the immediate vicinity of that location. So in the case of McMurdo, you have at the very top here McMurdo Base, but in the distance you can see towards the right there, that's Mount Erebus. So a very interesting scientific site to sort of explore. So you're near science right there. But you have to recognize that in the end, what is really driving Antarctic science today is only very little connected to Mount Erebus. Most of it requires you to range out to the rest of the continent, from collecting meteorites to studying the Antarctic range to understanding glaciology. And so in addition to this permanent base approach, you equip yourself with this multi-range mobility system. You've got C-130s for long-range access. You've got Twin Otters for shorter range hops. You've got helicopters in case you don't even need much cargo for short-range hops. And you've got even ground vehicles as well for both long range and short range. Short range might be skidoos. Okay, so you have this fleet, if you will, of mobility systems to enable your conquest, if you will, of the science of Antarctica. Now, at a very smaller scale, but still essentially following the same philosophy, we do work on Devon Island in the high Arctic. This is Devon Island on the left there. It's the largest uninhabited island on Earth. It's about the size of West Virginia. On it, you have Houghton Crater, which is a large meteorite impact structure. It's 20 kilometers across, 23 million years old. And the solid red circle shows you a 100-kilometer radius exploration zone around Houghton Crater, in fact, around our base on the northwestern rim of the crater. And the dotted red circle is sort of the 200-kilometer radius. So over the years, we've been operating at this site for over 20 years now. This coming summer will be our 22nd summer field season. We've operated out of a permanent base. So we have this base, it's there, it stays year-round. We don't occupy it year-round, but it's accessible every summer. And then we have a multi-range mobility system to give us access to these other locations. And I think this is, and this has proven to work really well. You, over time, have to bring less and less stuff each time you occupy the base for the summer because you have an infrastructure in place. And then now you're just talking about maintaining your equipment, and that's a very lean and mean approach, or it's an efficient approach to exploration. I should add that during Constellation, there was the notion that we would move the entire permanent base. So there was the permanent base, but there was quite a bit of discussion, which I found really hard to fight, to move the entire base over time. And the idea was to try to capture, I think, the benefit of a sortie mission, where each successive mission and crew going to the moon would actually land in a different location. And then in the meantime, in the intervals between missions, you would have the entire base crawl across the lunar surface, each element on a robotic platform. And I thought that was really a difficult concept to really realize in practice, because for one, it assumed that all your robotic platforms would essentially never break down, which I find difficult to believe. But the other thing was that it didn't have a very good Mars-forward application. On Mars, if you were to set up a base that was somehow crawling across the surface over time, you're now looking at something that would affect planetary protection. You would have all the activity and the microbial input that would come along with your presence on a base on Mars now crawl across the Martian surface over time. That can't be good for containing your microbial signature. So anyway, for what it's worth, this whole idea of suggesting a fixed permanent base with a multi-range mobility system comes from these types of experiences here on Earth. Now, analogs, if you analyze them, they essentially serve four fundamental functions. One is to learn, second is to test things, third is to train people, and then finally, and in fact the last one can happen all at the same time as the others are taking place one after the other essentially, you can engage the public and have educational outreach content. You learn at analogs, for example, when you are doing comparative studies, you're comparing two geologic features, for example, on the moon and the Earth, or on Mars and the Earth, and then you do a relevance analysis to figure out if this is really what you're seeing on the Earth is relevant, for example, to what you're studying on the moon or Mars. Testing is sort of a step above. You understand your site, you understand the fidelity aspects that it presents. It can be low fidelity in some ways, higher fidelity in the ways that matter to your test. You will scope your test, and then you proceed by trial and error. And so we've been doing a lot of the first two on Devon Island, for example, over the years. Training is something that whose time will eventually come. That's when you really understand the fidelity of either your site or the aspect that you want to test or train people on. You create an integrated simulation or sort of a set of conditions, and then you train your crew But not just your crew, also ground personnel. Mission operators should have a first-hand understanding of how surface operations are done. And also, of course, graduate students and students should also be part of this training pool. But that, again, is a sort of a separate function of analogs. And then, of course, engage, we've talked about that. So let's go over this in the case of the moon. The idea here for the moon is that as we go back to the moon, we should realize that there's an opportunity to prepare for Mars. The Mars forward strategy might be summarized this way. Use the moon as an analog for Mars in all four functions that we identify normally for analogs to optimize the shareable knowledge, the systems, and the operations that we would use on both the moon and Mars. So the idea is to not go to the moon without caring about Mars, the scenario on the left, where you end up with very little overlap between the knowledge, the systems, the ops that you would implement on the moon versus what you might want to do on Mars. So it says no, please. Instead, you want to try to achieve maximum overlap between the moon and Mars, okay, in your Mars forward strategy. And of course, the question is, how do you trade along the way between optimizing for the moon, okay, versus what might not be optimal for the moon, but might down the road on Mars buy you a lot. And so that's obviously a key trait in all this. So how will we use the moon to learn for Mars? Well, there's the science, of course. You learn from analog geologic processes and features. There are things here that are not common in terms of their details, but in terms of their general process and even features between the moon and Mars. The interior being differentiated, the role of impacts, the history of volcanism, the evolution of the regolith, the presence of volatiles in the regolith. All of these are not identical, of course, but they are relevant to each other, and you can learn from one to apply to the other at some level. The science ops is about identifying potentially shareable field science strategies, tactics, systems, instruments, tools that will be applicable to both worlds. And one example is sort of the exploration of lava tubes. It's a bit extreme. The idea is that if you are exploring with human crew some of these caves and pits on the moon, including lava tubes, well, not only are you gaining the lunar science of that exciting prospect, but you are setting yourself up with some background experience for exploring the similar features on Mars down the road. How would you use the moon to test for Mars? Well, the moon and Mars are different. For example, the thermal and vacuum conditions are different on both bodies, but some approaches and technologies can still be partly validated on the moon for Mars down the road. So one, again, somewhat extreme idea, but I think it's interesting, is one robotic way of exploring lava tubes on the moon would be to actually not use landers that would land directly into the pit, or rovers that would have to negotiate terrain that's unknown and face the very low temperatures of your lava tube, of your cave, and also the lack of comms. So one idea is to actually fly rocket thruster drones, of course small relative to the scale of your cave, in and out of your lava tube over time and have them fly back out to recharge, do a data dump from a lander, and then go back in so that they never get too cold to continue exploring. And so this rocket drone concept, which is being worked now with several different groups within NASA and with academic partners, could actually be the right solution as well for exploring lava tubes on Mars. You could not use airfoil drones in most lava tubes that we know of on Mars because they're all at very high altitude. They're on the flanks of the giant volcanoes. You are tens of kilometers in altitude. So even though we're testing a robotic helicopter on Mars very soon, which will be super exciting, we cannot really reasonably hope to use airfoil rotorcraft for exploring lava tubes on Mars down the road. So a rocket thruster drone might be the right way to do it. To test, use the moon for testing as well, we can do long-range exploration traverses on the moon, test this concept that's being proposed for Mars right now, but would be applicable to the moon, which is to define an exploration zone of about 100 kilometers around your landing site, and then see how over time it evolves into a real exploration zone with areas that can be traversed more quickly, others that are to be avoided, etc. We can then train crews for Mars. And of course, pressurized rover ops is sort of a glaring example. They're going to be key for human exploration of the moon and Mars. They're going to require a lot of training and practice on Earth to begin with. And then operations on the moon will add important experience for crews going to Mars. So a few years ago, this is the bottom slide in the middle, we drove the Northwest Passage in the Humvee that's on the bottom right. We stayed on sea ice at all times. It was sort of an epic journey. But this one leg that is shown here of 500 kilometers was traversed on very rough sea ice, unknown terrain at the time other than from this radar image. And it was traversed in 8 days. That same traverse projected onto the moon would take you from the crater Eratosthenes to the Apollo 15 landing site. Okay, so that's not to say that we accomplished that traverse, of course, unfortunately, but it does tell you that, from the standpoint of having this type of scale of operations on the moon from a fixed base somewhere is not out of the question, and you can actually cover a lot of ground if you have that kind of capability in just a week. So anyway, finally, you can use the moon to engage for Mars. Mars has, of course, strong public appeal. And the key thing, of course, is to really connect going back to the moon to moving on to Mars. So in conclusion, returning to the moon is an opportunity to better prep for Mars. The moon may serve all 4 functions of analogs for Mars. Given the multitude of analog potential, this calls for a systematic approach and process to really make sure that what we do is as applicable to Mars as possible. I can't believe that I'm suggesting that we form a committee, but seriously, it's a group or a process whose sole focus would be to ensure that our return to the moon optimizes relevance and preparation for Mars. Okay. Thank you.